Hello, welcome. This is the fifth question for AQA's AS Physics, I don't know, whatever paper this is, June 2010. Okay, so this is Unit 1. This question, question 5, starts off by asking us to kind of design an experiment. Although it's split up into two parts, and actually they would just ask you this as one. Okay, so 5A says a student wishes to investigate how the resistance of a thermistor changes with temperature. Okay, and all we're asked to do for 5A part 1 is draw a label diagram of a suitable circuit that would enable the student to measure the resistance of the thermistor. Okay, now all it is bothered about here is that you've got a working circuit including a power supply and a thermistor. With it, you also need an ammeter or a voltmeter, whichever one you decide to use. Okay, because obviously we're going to have to measure the resistance. Okay, so you could use V as IR and just substitute whichever component you've not got. Okay, now as I said, it might look slightly differently to the one that you draw. Okay, and they do accept. Basically, we've just, the most common one, and whenever it's talking about thermistor and increase in temperature, I would just use the example if it asks you to draw a circuit, because it is quite a common question about thermistor and the temperature changes, how that affects resistance. Okay, I would always draw it because what you need is something that starts at one temperature, and you can slowly increase its temperature, okay, without reacting with the thermistor. And obviously the easiest thing to do that with is in a water bath. Now the way you heat that is totally up to you, obviously, but the easiest thing to do is use something called an immersion heater, which is just essentially heating the water up. Okay, and obviously you can switch it off and on when you need to. Okay, but the key thing is you need a working power supply, so they're not that bothered, so it doesn't specify if you need a cell or a battery. In other words, what I mean by that is if you do one big line and a little line, you don't need to do one big line, little line, dot dot dot, big line, little line. That's a battery. Okay, it just says power supply, so it doesn't really matter. Okay, if you get it from the plugs, external battery pack, it doesn't matter. Okay, as long as you've got some power supply, they're not bothered. Okay, but as I said, the easiest thing to do would be just to draw some kind of cell. Okay, so just something like that. Okay, it's a very, very basic kind of cell. Right, so you just draw on the basics first, and then we'll start drawing on the ammeters and stuff. Okay, so your thermistor kind of looks like this resistor, but it's the one that has the hockey stick through it. Okay, and obviously that's connected like so. But we need to add a few more things on there. Okay, so it doesn't really matter as such where you put If you're going to put an ammeter, you can just put it, it doesn't matter if you put it over there or up there, but I'm not a big fan of using the ammeter, okay? See, I'll move this thermistor down a little bit so I've got a bit more room. I'm going to draw with the lid of the pen, that wouldn't have worked. Okay. Okay. Can't draw thermistor anymore. Really good. Okay, so there we are. So, as I say, I prefer thinking about it in terms of putting it in a water bath, but obviously you can control temperature now. In this part, it's not asking you to write anything about it just yet. So, just put clearly some kind of water bath around it. Okay, so it's my excellent drawing here. And then just kind of a little square thing, it doesn't have to be artistic. Okay, you can quite clearly see mine is not. Yeah, well, possible. Get art available with it. Anyway, so you just label it, obviously, immersion heater. Okay. And then obviously you would put that as the water. This is just my example, as I said. You could have done it in the context of we are going to need to increase temperature. Oh, this is measure a thermistor. Oh, sorry, it's not asking to increase the temperature, it's just a working circuit. You don't actually need this water bath stuff. But I mean, you're going to lose marks for it, especially, and it's going to help you to explain it in the next part. So I do apologise. You don't need this water bath, by the way, actually. Just a simple circuit that measures resistance. Okay, but I just put a water bath there because it helps me to explain the next part of the question. So then, obviously, what you need to do, I would put a voltmeter, okay, across it. Now you could put the voltmeter at the terminals of the battery. Totally up to you. You'd only really have to put it if you included another single fixed resistor. But seeing as we haven't. It doesn't matter if we put the voltmeter there or if we put it across the terminals of the battery. Okay, doesn't really matter. But I would always put it over the immersion heat. Sorry, I would always put it over the thermistor. So obviously you label this as the voltmeter, and I would label that as the thermistor. And I would put the battery, and then you might want to put, just to be sure that you've got the marks, the power supply. Okay, so that's 5A part 1, a very, very simple question. Okay, simply just drawing a circuit. I probably made it too complicated there. As I said, it's just asking for a circuit with a thermistor in it where you can measure the resistance. Okay, so you could have just not bothered with the immersion heater or the water bath, and simply just drawn the voltmeter measuring the potential difference over the thermistor. You didn't really have to bother with all that, but I just thought I'd try and show off any artistic flair that I don't have. Okay, so anyway, 5A part 2 says, describe the procedure the student would follow in order to obtain accurate and reliable measurements from the resistance of the thermistor at different temperatures. Now, this is why I've drawn the water bath, because it helps to put you in the mindset of how you're going to explain this. Now, with all these kind of 6-mark questions, it's not about writing tons and tons. They are, I think I say this in every 6-mark question at AS, you can and at A2 for that matter as well, you simply just put bullet points. You don't need to write a full essay. It does put people off because it says the quality of your written communication will be assessed. All that means is, can you spell right, and do you put capital letters and full stops in the right places? So don't turn it into an English exam when it isn't one. You're taking physics, not English. You're smart, not dumb. Well, saying that, that's why I couldn't take English. Anyway, apart from that. So obviously with all these questions you need to show your method and how you work it out, but because we've already drawn the diagram, obviously you don't get any marks for the diagram. So in this 6-mark question, it's still a 6-mark question, you have to note that it also asks you, you also need to state how you're going to collect your results as well, in terms of you need to put in a table, etc, etc. So just add a bit more to it really. Okay, so yeah, and also as you're going through this as well, sorry, I just had to double check I was right. You're going to talk about how you're going to keep the temperature the same, okay, and any errors you may encounter and how to keep them. Because as I said, this is a 6-mark question where the 6 marks are not contributed to the drawing of the diagram, so you need to do a bit more analysis than you might normally do. Okay, so obviously the first thing that I would say is to measure whatever it is in terms of whatever equipment you're using. Okay, so if you've got the voltmeter, then obviously I'm putting it down. So I'm going to measure the potential difference across the thermistor, obviously. And because I said you've got to encounter errors, okay, I would say I'm going to measure the potential difference across the thermistor at when the circuit is not complete. Okay, so you can therefore take out any systematic errors across the thermistor when the circuit is not connected. Okay, so as I said, you didn't really need to put that. I don't think you do, but it's just to show the examiner you are considering errors. Okay. So it's asking you to show how the resistance of the thermistor it changes at different temperatures. Now you should remember the two types of coefficients that we've got to deal with here. Okay, obviously you've got the positive temperature coefficient, which says that resistance increases with temperature, and the negative temperature coefficient, which says resistance decreases as the temperature increases. So it's just the relationship between the two. Okay. It's not asking you to state whether it's a positive or a negative temperature coefficient, but you should know obviously that a thermistor has a positive temperature coefficient. Okay, so that obviously, as we've said, that means as the temperature increases, resistance will also increase. Okay, so that's what we're expecting to see, and you need to state that later on, but we need to build up to that. Okay, so obviously the first thing we do, as I said, would this might not be your first point, but it's the first one I did, just so you could check for any systematic errors, and I would make that clear in your first point, so that'd be to check for systematic errors. Now this wouldn't necessarily matter because the correlation will be the same. In other words, gradient will be the same whether there's a systematic error or not. So maybe you didn't need that so much. Anyway, so the next point you would do is you would go, okay, well you would choose a regular increase in temperature. Now quite a common one might be 10 degrees, for example. I'm going to take a few readings, okay? So say something like, every 10 degrees C, record the value on the voltmeter. Okay. So obviously, actually, what do you need a meter for? Yeah, actually. Well, it depends. If you knew the current of this, would you? No. Do you need to know the? Not 100% on that one actually. Yeah, okay. So assuming you knew the current, alright, so you might put an ammeter in there as well. But as I said, it's totally up to you. Actually, I'm going to put an ammeter there as well. Okay, so I know I didn't do that before, but what are you going to do? Okay, put an ammeter there. So every 10 degrees, record the value on the voltmeter and the ammeter. Okay, and obviously you would explain that you would heat up the water through the immersion heater. I just haven't been bothered to write that down. Okay, so you would say you would repeat this step until you get to a certain value where you've got enough results. And you might want to say as well, repeat the experiment to get an average. Okay, so once you've said how you're going to record your results and how you're going to increase the temperature, okay, the next few points are about how you're going to plot your results and what graph you're going to use. Okay, now it says in the mark scheme that a good graph to use would be one for resistance against temperature. And if you were to do that graph, what you would have to do for your next step is say, using values recorded, using recorded values work out the temperature, work out the resistance at each temperature. Okay, and then once you've done that, if say you might have already mentioned that point when you talk about recording the value of the current and the voltage or potential difference. Okay, so once you've done that, then obviously your next step would be to plot them on a graph. Okay, so you would say plot a graph of resistance against temperature. Okay, and obviously because we've got a positive temperature coefficient, it should be a positive relationship between temperature and resistance, so we get a positive constant gradient. Okay. And it says you might give some indication of how much temperature change you're going to do. So we said every 10 degrees C, record the value on the voltmeter and the ammeter. You might say up to a value of obviously 100 degrees be a maximum. Okay. But then you just say, well, you would use that to work out, just to prove that it's got a positive temperature coefficient. You just explain that. But really, that's all you need to do for 5A. But weirdly, that's not the end of question 5. Okay. Normally, on a question where they ask you to do a big explanation, they kind of end it there. But unfortunately for us, they don't. Okay. So again, it's another little diagram we have to draw. Well, not that we have to draw. I have to draw. Sorry. Just be a second. Yeah. Pause the video. Just draw it on for you. Hello, welcome. This is 5B part 1. Okay, so I've drawn the basic circuit on the board. I mean, it's not the best, but at the end of the day, you've got the ability to look online. Anyway, so we're told that when the temperature is equal to 50 degrees C, the resistance of the thermistor, is 1.2 kilo ohms. Now, you need to convert that to, weirdly enough, single ohms. Otherwise, it obviously would affect your result. So, obviously, that's 1,200 ohms. Okay. We're also told that the voltmeter across this fixed resistor R reads 1.6 volts. So, in other words, the potential difference across R is 1.6 volts. What it's saying. Okay. So, we're also told that the battery has an EMF of 6 volts. Now, you can't... Now, let's just take into... But we're told that there's no negligible internal resistance. In other words, little r is equal to 0. So let's just take into account... Just take a step back a second and think... Well, you might... I mean, you could get this question right purely by look, okay? But you need to just understand why this is. EMF is not equal to potential difference. So even though they're both measured in volts, they're not the same thing. EMF takes into account the internal resistance as well. So in other words, the EMF is equal to V plus I little r. Or in other words, the EMF is equal to I, the current, times big R, the total resistance of the circuit, plus the current times the internal resistance. But as the internal resistance is equal to 0, IR is equal to 0. Okay, so the EMF is equal to the potential difference. So you can just imagine the EMF is equal to potential difference. And we can do that because there's no internal resistance. But if there was internal resistance, obviously we couldn't. But as I said, you could have just got this right purely by look, reading the 6 volts as the potential difference anyway. Okay, but it's clear to make that distinction. So anyway, 5B part 1 says, calculate the potential difference across the thermistor. Well, it's all about knowing your knowledge, okay, about, well, what happens to potential difference? Well, it's shared, okay, so the potential difference across R plus the potential difference across the thermistor is equal to the potential difference across the terminals. In other words, the potential difference of the battery, okay, now we said it's 6 volts, and you can say that EMF is equal to potential difference because there's no internal resistance. Okay, so you know 6 volts is total potential difference is equal to the 1.6 volt that's going through the fixed resistor plus the potential difference, I'll just put PD, of the thermistor. Okay, so you just sub it and then rearrange it and say, well therefore the potential difference of the thermistor is 4.4 volts. We're asked now to calculate the current in circuit. Here we go. How the hell are we going to do that? Well, let's just take into account what we know. Okay, so what can we do to work out the current? Okay, well, the easy one to do would be say, V is equal to IR. But we couldn't do that for the terminals of the battery, even though we say E is equal to V, so therefore the EMF is equal to IR. As V is equal to IR, we said the EMF was equal to the potential difference when there is no internal resistance. However, that R, remember, for the whole circuit is for the whole circuit. But we don't know the resistance of this fixed resistor. The only purpose of it being there was to enable us to work out the potential difference across the thermistor. Okay, so we can't use it across the terminals of the battery, and the reason for that is because we don't know the resistance of the fixed resistor, so we can't use that either. I probably should have said, obviously, the other equation you could have used, because P is equal to IV, you could say, therefore the current is equal to the power over the potential difference, but we don't know the power, so we can't use that equation. So I'm hoping you got straight away, we just went using V equals IR. Because we're not giving anything else about any power ratings or anything. Okay, so what we can do now is say, well, we know the resistance of the thermistor, okay, so we're not changing the temperature. We haven't used these two bits of information yet. So that when the temperature is equal to 50 degrees, the resistance of the thermistor is 1,200 ohms. Well, obviously, that's the resistance, we'll label that as R. But remember, that's just the resistance of the thermistor. And we just worked out in the previous part of the question that the potential difference across the thermistor, okay, we're not changing anything about the situation, it's still at 50 degrees, okay? So the potential difference across the thermistor is 4.4 volts. So we know the potential difference of 4.4 volts. We don't know the current, obviously, but we know the resistance, which is 1,200 ohms. So we can sub all that information in to V equals IR, okay? So the current is equal to 4.4 volts over 1,200 ohms, which I'll just sub into your calculator. You should get about equal to 3.7 times 10 to the minus 3 amps, obviously. Now you may go, well that seems ridiculously small for a current. Well, don't be put off by such a small number. It's logical because you think, well, because V equals I, we obviously overall can't change V. And I know we said that the EMF was not equal to potential difference, but it is, as I said, when there's no internal resistance, because the EMF is equal to V plus IR, R being the little internal resistance of the circuit. So therefore, as I said, we can say that the EMF is equal to the potential difference of the circuit. Okay? So therefore, what we're saying here is the potential difference, even though it really states as the EMF, is 6 volts. And 1.6 of them volts is already taken up over the fixed resistor. Okay? But the therefore the remaining 4.4 volts must be attributed to the thermistor. And because the thermistor's resistance value is so high of 1,200 ohms, okay, to give a value of the potential difference of 4.4 volts, because the potential difference of the thermistor, remember, plus the potential difference of the fixed resistor must add up to the potential difference across the terminals. In other words, because they're the only two resistance components that are in the circuit, we ignore, as I said, that we can ignore that there is any internal resistance at all, because there isn't any. It does exist, but it's negligible, so that obviously means that it's so small it wouldn't really matter that we put it in, okay? It wouldn't really matter, it's that small. Okay, so anyway, you think, well, we've got such a high reading for our resistance and a relatively low reading, specifically in comparison to the resistance, and as V equals IR, that must mean if we have a really high R value, we must have a really low current value to have a sort of low-ish potential difference value. If that makes some kind of sense. So that makes sense. If we had something that was bigger than what you're saying is 1,200 ohms times 1 is 4.4 volts. Well, it clearly isn't. We need something a lot less than 1, hence something times 10 to the minus 3. Okay? So hopefully that makes sense. And as I said, don't be put off by such a small figure. Try to give you a bit of explanation why it can be so small. But as I said, if you just accept the fact, just using standard equations, it's totally acceptable. Okay, you don't really need to know that. I've probably waffled on too much. Okay, right. So that's the end of moving on to 5b part 3. Calculate the resistance of R. Now I probably want to rub off these crosses because I've not actually got rid of them. Just put them there because I was halfway through my explanation, getting so into it, I forgot there was another part of the question. Anyway, so it's asked us to calculate the resistance of R, quoting your answer to an approximate number of significant figures. Now for this, the way I've worked this out, I personally, this value of the current, which is about 3.7 times 10 to the minus 3, actually that's a rounded figure. It's more, when you type that into your calculator, 4.4 over 1,200 volts, you get something like 3.66, and it continues and continues from it until you get to the 7, and then times 10 to the minus 3. So basically that's a quite a rounded figure, and if you work it out, it's a little bit of a difference. So I would always just leave that as your answer. So store it in your calculator's memory, in other words, and save as your answer button. So when you hit the answer and you hit equals, you get this 3.666, etc., etc., times 10 to the minus 3 amps, obviously. So we need to calculate the resistance of R. Again, this is very, very easy. Okay, so 5b part 3. So what do we know about R? Well, we know that because we're told previously that the potential difference across R is 1.6 volts. Okay, because that's what the voltmeter reads across R. So therefore, that's what the potential difference of R is. Okay, and as we know, V is equal to IR. And we know, well, obviously we know the current. We've just worked out the current. The current is the same throughout the circuit. Okay, if it was in parallel, okay, then the current would be split. But because it's all in a series circuit, it's the same anywhere in the circuit. Okay, so we use the exact same value of the current that we got for 3b part 2. So I would sub that exact value into current, which is 3.66, etc., etc., times 10 to the minus 3. And that's times by the resistance value R. And then it's just a case then of rearranging it and, in other words, dividing both sides by this 3.66 times 10 to the minus 3. Okay? So you will get a resistance value for the fixed resistor of about 440 ohms. Okay, which again makes sense because we know the current is very small and the potential difference is fairly small, so we need quite a large resistance value. Not as large as the thermistor, obviously, because that's a much lower current, is much higher resistance. Okay, so anyway, that's the end of the calculation questions. This last little bit, 5c, is again it's just a knowledge question. You either got it on the exam or you didn't. Generally people didn't half get this question. Okay, so it says state and explain the effect of the voltmeter. On the voltmeter reading if the internal resistance of the battery in part B was not negligible. So in other words, what would all of that equated to in terms of this voltmeter here? Basically, how would the potential difference of the fixed resistor R have been affected by if we included the internal resistance? Okay, and now there's a couple of ways of going about this. Obviously, it's just simply a wordy question, but if you've got a bit of time in the exam, I might recommend simply just subbing some numbers in and working all this out again. But then, many people didn't have that luxury of time. Anyway, so simple factors of saying if there was internal resistance, okay, then we'd use our EMF equation of the EMF is equal to the current times the resistance of the whole circuit plus the current times the internal resistance, which we label as little r. Hence, as the EMF is constant, because obviously the EMF wouldn't change, we're just including the internal resistance now. the current would have had to be lower because the resistance of the whole circuit cannot change. All we've done is increased we've added resistance into the circuit. Now, bear in mind, it doesn't really matter that's in a form of internal resistance, okay? It's still resistance. Resistance is resistance. It doesn't matter if it's from the internals of the battery or if it's from a component in the circuit. It's still resistance, okay? So we're still adding to resistance. And if we add to resistance, okay, then the current drops, okay? That's logical. So the current will drop due to increase of the total combined resistance. Hence, the reading on the voltmeter should fall. And that's because if we're saying that this R is a fixed resistor, yeah? And because we're increasing the total resistance of the circuit by introducing this internal resistance, okay, as V equals IR or E equals IR plus I little r, okay, we are therefore increasing total resistance, so therefore current must decrease. And if current decreases, well, this value of the fixed resistor we assume to stay the same. So as V equals IR, the potential difference, equals the lower current times the same value of resistance for that fixed resistor because it is fixed. Therefore, logically, basic maths dictates that the reading on the voltmeter should fall. Now, I've made myself sound like a posh twat then, and I do apologise. But at the end of the day, what are you going to do? Absolutely nothing. Apart from maybe attack me in the street, but hopefully we don't come to that. Okay, because you get your AAA star in physics because of me. So if you just put this video on, just put it, just rip me off in terms of, oh, that sounds weird. Put it on a DVD, just put it inside your exam, go, there you go, he's done the exam for me. A star there, very good. Okay, so thanks for watching, hopefully it's been helpful, and we'll see you in question 6.